Hello everybody, welcome to this lectures in linear systems theory. So, we continue with our discussions related to transformations, and what we had left as topics to be discussed in this lecture was starting with invariant subspaces and see the concepts of or learn the concepts of eigenvalues and eigenvectors. Okay, so what is an invariant subspace, and this is a very interesting concept. Perhaps the name might tell you something already, and if you maybe take a course on nonlinear control after this, much of the stability analysis would talk a lot about invariant subspaces, even good implications of it while we study stability in the linear sense and sense also. So, okay, what is the definition of this? So, I have a map F from V to V, and I have a subspace W of V. So, okay, let me just draw some pictures here. So, this could be my V. I have a little W sitting here. So, I take any vector x, okay, belonging to W. So, it's not here, right? It's inside here. This vector x, when acted upon by F or transformed by F, will again sit in the same subspace. Okay. So, when this happens, that okay, there is a subspace, there is a V and W is a subspace of V, then if something like this happens, that I start with a vector x in W, okay, then I have that f of x is also in W. Okay. Now, it is then said that W is invariant under the transformation F, or W is F invariant, right. It could not be, there could be vectors which start from here and jump here and vice versa, but this specific class is called that W is F invariant. Trivial examples, if map from Rn to Rn, it's always, you know, Rn is a trivial subspace, right, and then the other one is the origin or the 0 vector, right. You take 0 and you multiply anything by 0, so to speak, you will always get a 0, right, because the transformations are usually of the form matrix. So, if I take the 0 vector and I have the transformation A, I will always come to 0. This is also to do with so what we call as the equilibrium, right. So, if I say, well, what is the property of equilibrium? Well, if I am at equilibrium, I am always at equilibrium, assuming that there are no external perturbations. So, the equilibrium, so say for example, if I just write x dot t is a x t, or in the discrete time as x k plus 1 is a x k. Okay. So, what does equilibrium mean? That this transformation A, if applied to the equilibrium, the system will still be at equilibrium. What does that mean in terms of solutions? So, what is the solution of this equation starting from an initial condition x of 0 equal to 0? It will always be in 0. Any other initial condition, the way the system behaves will depend on this matrix A, right. So, similarly for here, right. So, if the initial condition is 0, this transformation will be at 0. So, the origin is also an invariant subspace. Okay. This might look trivial subspace, but in general it is not, and we will see why it is actually a non-trivial subspace, even though okay, here mathematically it might just see that okay, if I am 0, I multiply 0 by something, I will always be at 0. Okay. But there could be other things, right, which are like non-trivial subspaces. So, when can we find non-trivial W given an F? And this is where we begin now with the concept of eigenvalues and eigenvectors. Okay. So, first okay, I am sure we would have read this somewhere, but we will slowly try to revisit and see what would it mean a bit geometrically. Okay. So, the statement here says that eigenvector of a linear transformation is a non-zero vector which only scales and does not change direction when this linear transformation is applied on it. Okay. So, typically if I take a linear transformation A and apply x on it, I might get some other arbitrary vector, right. So, this vector could be different in magnitude and different in direction, right. However, an exception happens in this case. So, if I write this statement mathematically, it will look something like this, right. So, just concentrate, let us concentrate on this one. The matrix representation of this F is A, and this A is such that when it acts on a vector x, it gives me lambda times x, right. So, here this lambda we can simply assume it to be some real number. Okay. So, what does it do? So, I give you a vector x, this matrix A. So, if say maybe something like this is vector x, right. Okay. Now, what does the lambda do? It can just sorry, if lambda is say -1, it will just give me this number. Lambda is 0.5, it will just give me a vector half the size. Lambda is 2, it will just give me a vector which is maybe twice the size, right. So, what does it do? That so the vector retains its direction. And if I just look at the vector representation or the geometry of this vector x when multiplied by A, whenever it is equal to lambda x, it means it is just the same vector, just that it is just multiplied by a scalar, right. So, the direction is retained, just the magnitude might change. Only thing it can change direction is this one, right, with the -1 direction. Okay. So, so this is the a little interpretation of an eigenvector, okay. And given any square matrix A n cross n, I can always find things like this, okay. And there could be cases, okay. So, in this expression, this lambda is what is also usually known as the eigenvalue, right. So, for a given relation like this, we can call that lambda, right, this lambda known as the eigenvalue associated with the eigenvector x. Well, there could be multiple eigenvectors associated with a single eigenvalue, and all those variants exist. Okay. And these eigenvectors are invariants under transformation F. What does it mean? Just it's the same here, right. So, take a vector x coming from some say some Rn or maybe whatever, I multiply this by A, I get lambda x. So, if x is in say some Rn, this you multiply a vector in Rn by a number, this will also be in Rn. So, it means that eigenvectors are invariant under the transformation F, and you can just compute the eigenvectors. It is a very simple exercise of computing eigenvector of a matrix which is given by 7 3 3 minus 1. Okay, we will not go into the details of the computation. Okay, so where does this expression come from? So, I start again with Ax is lambda x, which I can write as Ax minus lambda x is 0, or A minus lambda I, where I is identity matrix of appropriate dimensions equal to 0. Okay. So, what does it mean that x is in the null space of A minus lambda I, or the kernel of A minus lambda I. So, and we are not interested literally not interested in so we are interested in a non-trivial solution of this. Okay. So, which essentially means that my A matrix or this matrix A minus lambda I should be a non-singular matrix, which turns out mathematically to saying that the determinant of A minus lambda I should be equal to 0. And this equation is also referred to as the characteristic equation of a matrix A. Okay. The roots of these equations are called the eigenvalues. They may be distinct, they may be non-distinct, they may be real, they may be imaginary, it might be a value 1, it might be value 0, and so on. Okay. And the corresponding eigenvectors are again the non-zero solutions of the linear system of equations A minus lambda I n times x equal to 0. An important property here is that the eigenvectors corresponding to a distinct eigenvalue are linearly independent, but the converse may not be true. We will shortly do an example related to this. Okay. So, there is a theorem here which we will use while we do controllability and other stuff, or even computing the matrix exponentials. I will not do the proof of this, but it just says that every square matrix satisfies its own characteristic equation, which means that okay, start from here, determinant of A minus lambda I equal to 0 will just result in a polynomial of this form. So, I will have a A1 lambda power 1 and so on. So, I will get a polynomial of order n in lambda. So, this is the characteristic equation. What does the Cayley-Hamilton theorem say is that if I just replace this, loosely speaking, this matrix by A, so this, replace lambda by A, I just have A n minus 1 plus A 0 I n. This is also true, that the matrix A satisfies its own. So, when I say this characteristic equation, what am I looking for? I am looking to find solutions lambda, and if you just replace lambda by A, the equation still holds. We will postpone the proof till a little later. So, when next time when we encounter the use of Cayley-Hamilton theorem, we can just take a little detour, do the proof and come back. Okay. There are some other properties of these eigenvalues. So, this is the standard way Ax equal to lambda x is usually called the right eigenvector of A, and whenever we say eigenvectors, it by default is the right eigenvector. However, there could also exist what is called the left eigenvector associated to the eigenvalue lambda, which is represented by this one. Y transpose of A is lambda of y. Again, this transpose and all comes for obvious reasons, right. Okay. It is also possible to choose these y's, y1, y2 and so on, which are the left eigenvectors and the right eigenvectors, such that, well, they either in such a way that y times x equal to 0 or y times x could also be equal to 1. And this again, so how do we do this? Well, we can look at those transformations which we did earlier. Okay, so there should be a transpose here. Okay, sorry about that. Okay, some little more properties of eigenvalues and vectors. Some of them we will do the proof, some of them okay, I will just leave it to you as an exercise. So, if lambda 1 till lambda n are the eigenvalues, the determinant of A is just the product of all the eigenvalues. Now, there is another quantity called the trace of A. For a square matrix, it just turns out that the trace is the sum of all the eigenvalues of the system. Okay. Then if A has eigenvalues lambda 1 till lambda n, A transpose will also have the same eigenvalues. I think the proof here should be similar. So, if lambda 1 till lambda n are the eigenvalues of A inverse will have the eigenvalues corresponding to lambda eigenvalues as lambda 1 inverse till lambda n inverse. Well, let us do a couple of this quickly. So, I have A times x is lambda times x. So, I am looking at say the inverse, right. So, here assuming that the matrix is invertible, so A inverse A x is A inverse lambda of x. So, this will be x is A inverse lambda of x, or I can rewrite this as A inverse of x is lambda inverse of x. again assuming that none of the lambdas are 0, otherwise this will not hold. Similarly, I can find out what, so that the of this statement, right. So, so A x is lambda x. So, I can find out what are, so how do these relate to the eigenvalues of A transpose. So, let us start from here, take the transpose. So, this will be x transpose, A transpose is lambda times x transpose, and if you look at it, this is similar to this expression. So, it means two things here. One is that the eigenvalues remain the same of A transpose, and whatever was the right eigenvector of A is now the left eigenvector of A transpose. This is not surprising, right? Even this expression tells us the same. Yeah, but the important property is that the eigenvalues of A are equal to the eigenvalues of A transpose. Okay, so if I take a matrix A, I multiply it by lambda, the eigenvalues will be scaled up by lambda. I will not do the proof of this. Similarly, if I look at say given a matrix A, what are the eigenvalues of say A square? Okay, so let us start with A. So, again I have A x is lambda x. If I do A of x, what is this? This is A of lambda x. Now, this is again I can rewrite as A, so lambda A x is, what is A x from here is lambda x. So, I will have lambda square x. So, I have one relation which says the following, that A square x is lambda square x, which means that that lambda square is an eigenvalue of A square, and I can still do it till p. So, A p, if I take a particular eigenvalue, so this will be lambda p times x. Okay. Now, lastly, if q of x is a polynomial in x, then q of lambda 1 till q of lambda n are the values of q of A, and this actually can be viewed as some kind of version of or an application of the Cayley-Hamilton theorem. Okay. So, some other important things, like really the special cases of eigenvalues. So, if eigenvalue is 0, okay, so this is corresponds to lambda equal to 0. So, which essentially means that A times x will be 0. So, this means that x, which is the eigenvector, is in the null space of A, and this x is non-zero. If you look, so we are all the time interested, or most of the time interested in non-trivial eigenvectors. So, which means that there exists a non-zero, or a non-trivial null space to A. So, what is a trivial null space? X equal to 0, right? If x equal to 0, A times 0 is 0. This is a trivial null space. It maps origin to origin if I look at it in terms of transformation. But whereas, if there is an eigenvalue of 0, then there exists a non-trivial null space to A. This also means that whenever there is a 0 eigenvalue, that this matrix is not invertible, or it is or it is also called as a singular matrix, or the determinant is also 0, right. Okay. Interesting thing also happens for the eigenvalue equal to 1. Okay. So, so if I have lambda equal to 1, then I end up with this A times x, which is lambda x is equal to x. Okay. if I look at this, so it can mean few things, right. So these transformations, so these are called the fixed points. So what happens if I take a square of x, right. So a square of x will be a of x. What is a of x is again x, again a of x is again x. So similarly you can do a n of x will still give you x, and therefore these are called the fixed points of the transformation. So how many ever times I apply the transformation, I just remain at x. Okay. So an interesting case is, okay, what when A is the identity, say the n cross n identity matrix. Identity matrix will have lambda equal to 1, this is a trivial thing. And what are the eigenvectors? Well, all vectors or any vector, right, all vectors are the eigenvectors. Corresponding to lambda equal to 1. You can just check that. Okay. Now, once we have these vectors, it is natural to associate them to a space, right. So, if I extract 2 or 3 vectors, and I will just be interested in what kind of space do they span. So, that leads us to defining the concept of an eigenspace. Okay. The eigenspace of a matrix n cross n, so it corresponds to eigenvalue lambda. So, given an eigenvalue lambda, so the eigenspace is a space spanned by all vectors of A corresponding to that lambda, referred to as the lambda eigenspace. So, in a way that a given lambda or a given eigenvalue can have more than one vectors. So, as a trivial example, look at say a 3 cross 3 identity matrix I3 with lambda equal to 1. Any vector in R3 is an eigenvector, but what is the space that they span? They span a 3-dimensional space, and therefore the eigenspace of this lambda equal to 1 is just R3. Trivial example, but useful to understand what this statement actually means. And this is actually a subspace of Rn. Why is it a subspace of Rn? Because, well, look at this relation, right. This lambda eigenspace is a subspace of Rn as it is the null space of A minus lambda n. And we saw earlier that this kernel and image were actually subspaces in the week 2 lecture. Okay. And not only that, this eigenspace is an invariant is an invariant subspace under the transformation A. That is also easy to check. And what happens if lambda is 0 for the 0 eigenvalue, then this space lambda of A is just simply the null space of A. So that was again easy to check, right. A x equal to 0 was the case when lambda equal to 0, and the set of all x will constitute the null space of A, and this null space is the eigenspace corresponding to lambda equal to 0. Okay. Just a little concepts defined and then relating to what we studied earlier in terms of vector spaces. Okay. Some just this could be a little dry, but it's useful to know a bit of this these definitions. So one thing, okay, we start with algebraic multiplicity. That's maybe a little easier to comprehend. So the algebraic multiplicity of an eigenvalue lambda of A is the number of times lambda appears in the root of characteristic equation. Again, if I take the 3 cross 3 identity matrix, the algebraic multiplicity would just be 1. If I look at In as my matrix at hand. So the geometric multiplicity similarly of eigenvalue of A is the dimension of eigenspace, right. Again, what was the if I look at I3, okay, just so I3, the 3-dimensional identity or the 3 cross 3 identity matrix had an eigenvalue of 1, and what is the dimension of its eigenspace? Well, the dimension of its eigenspace was also equal to 3. Okay. So its geometric multiplicity was 3, algebraic multiplicity is also 3. In general, it could be the number of independent eigenvectors associated with an eigenvalue. So this word independent is important, right? So what we said for the I3 matrix is that any vector in R3 is an eigenvector, but how many of them can be independent of each other, which we take any standard basis, it will just be 3, and the remaining vectors can always be written as some kind of linear combination of these 3 vectors. So the dimension or the number of independent eigenvector associated to this eigenvalue would at best be 3. And so this is like a trivial example, right, where the algebraic multiplicity coincides with the geometric multiplicity. Okay, so I should write a 3 here. Okay, so in general they can be different, but what can happen is the geometric multiplicity can be at most equal to the algebraic multiplicity, right? If this is 3, this can never be 4, it can at best be 3. And of course the sum of algebraic multiplicity of all eigenvalues of n cross n matrix is n. So let us say I have say lambda n with a multiplicity of n1, lambda 2 with a multiplicity of n2, lambda 3 with a multiplicity of n3. I am talking of the algebraic multiplicity. So in an n dimensional space, this n1 plus n2 plus n3 will always be equal to n. This is not surprising, right, because I am just counting all the number of eigenvalues. Okay. So an important property whenever we talk of eigenvalues or in general of matrices is about diagonalizing the matrix. So we spend a lot of time doing that in our math 1 or 2 courses. I mean, if people had followed books like Greywall or something, there was lots of things on diagonalizability of matrix, which was also kind of used to solve equations by elimination methods. Okay, so the thing is we never ask ourselves, can we always do that, right? Just given a problem, I just apply the standard techniques and try to diagonalize. Now the question is, when can I actually do that, right? So if for every eigenvalue of A, if the geometric multiplicity equals the algebraic multiplicity, then A is said to be diagonalizable. So there is also then a counter question of what if the algebraic multiplicity and geometric multiplicity are not the same. Okay, we'll keep that question for a little later, maybe in the next 1 or 2 lectures we will try to answer this question. But this is a very important property to know. We always were talking of diagonalizable matrices without really understanding if I can always do that. We'll do examples and counter examples to this in maybe also one of the tutorial classes. Okay, as an example, let's do this, right. So the question is to find geometric and algebraic multiplicity of all eigenvalues of A, which is this one. So I'll just skip the computations, but the eigenvalues here are lambda equal to 1 and 1, which means the algebraic multiplicity of lambda is 2. Okay, now what is the geometric multiplicity? So I'll just find the set of all eigenvectors associated to this eigenvalue. Okay, so let's do this. So I have A, which is 1 1 0 1 minus lambda, which is 1 times the identity 1 0 0 1. Right, so this is what I look at, right, like A minus lambda I times x equal to 0. This will give me a 0 here, a 0 here, minus 1 here, no, sorry, 1 here and a 0 here, and times x equal to 0. So this we are in R2, so let's simplify this and write this as 0 1 0 0 x1 x2 equal to 0. So what are the possible x's here, or what's the possible x1 and x2? So the only equation or only thing I can infer from this is x2 equal to 0, and therefore any vector of the form x1 0 is an eigenvector. Okay, now what is the span of this? The span of this will just be a one dimensional subspace, right? Okay, now let us go back to the definition of the definition of algebraic multiplicity is simple, right? Just find how many times lambda equal to 1 occurs. The answer is 2. So, the geometric multiplicity is the dimension of the eigenspace of this one, or the number of linearly independent eigenvectors. So, how many linearly independent eigenvectors I can get is just 1. So, I can take x1 or multiples of x1. I can just say, okay, this is an eigenvector. Any other eigenvector would just be a multiple of this. It could be 4, 0, minus 4, 0, and so on. Okay. So, the geometric multiplicity here is 1 and the algebraic multiplicity is 2. So, this a little example to show that to validate this statement, that they can be different and add. So, this does not need a proof. It is a little easy to understand that the geometric multiplicity can at best be equal to the algebraic multiplicity. Okay. So, just a little example, or if you remember one of the examples which we did when we were looking at building consensus algorithms in a wireless sensor networks, or do they converge to some value, and we talked about some properties of matrices and how they converge to certain eigenvector. Okay. So, I will just do a little, not really a proof of what was happening there, but give a little intuition behind why that algorithm converged to a certain value, which was the average of all the initial conditions. It is just from the week 1 lectures. So, this also is maybe an example straight from Gilbert's ranks, where he motivates by saying, what should I do if I want to compute given a matrix a power 100? Do I do it 100 times? Right? That will be computationally expensive. Now, are there easier tricks to do this? So, you just redo that example here so that we understand of where we are going from here. And again, at each point of time we will try to give it a system theoretic explanation. Okay. So, the matrix he uses there is A is 0.8, 0.3, 0.2 and 0.7. So, if you look at it, the columns add up to 1. Could be a little relevant to what we had, the statements that we had earlier. Okay. So, this has eigenvalues of lambda is 1 and lambda as 1 by 2. Okay. And the corresponding eigenvectors of 0.6, 0.4 and 1, minus 1. Okay. So, what was also so we earlier said that if lambda is the eigenvalue of A, then lambda square is the eigenvalue of A square. Well, what is eigenvector? Eigenvector of A square or A square has the same eigenvector as A. So, A square, sorry, I will just write it a little nicely. So, this maybe we didn't mention it earlier, but A square has the same eigenvector as A. Okay. Okay. It is just a little thing which we would have missed earlier. Okay. So, now what does A power 100 look like? Well, A power 100 apparently would look close to something like this, 0.6, 0.4, 0.6, 0.4. Okay. So, if I just were to make a wild guess of how do I compute A power 100 or higher powers, that as the powers go large and large, the columns converge to the eigenvector corresponding to the eigenvalue lambda equal to 1. And lambda equal to 1 was also an eigenvalue in that wireless sensor network problem. Okay. Now, we will do a little proof for this. Okay. So, let us say, okay, so how do we go about doing this? So, this column 0.8 and 0.2 can be represented as, well, in terms of its eigenvalues and vectors, as x1, which is the first eigenvalue, plus 0.2 x2, okay, which is simply say 0.6, 0.4 plus the vector x2 is 1 minus 1, this will be 0.2 and this will be minus 0.2. Okay. Now, the 100th power of a, the first column would just look something like this, a power 99 with 0.8 and 0.2. Now, with all the properties of a square and lambda square, a cube and so on, we can write this as the following. This will still be x1 because lambda 1 power 99 will still be 99 plus (0.2) times lambda 2 power 99 times x2. Again, some you can just rewrite these things and it will come show up here. Now, this is arbitrarily close to 0, right? Maybe the first digit will show up after some 20, 30, 40 decimal places, and therefore, a power 99 times 0.8, 0.2 would simply 0.6 and 0.4. Similarly, with the second column also, right? Okay. Now, why does it happen this way, right? So, there are two terms here now if I can look at it. So, if say assume that maybe this is the system matrix of a dynamical system of like this, right? A comes from a dynamical system 0.3, 0.2, 0.7 times xk. Okay. Now, I can ask myself of what is the steady state value of x starting from say some non-zero or non-trivial initial condition. It turns out the following, right. So, I have something here which just it just beats the way it is, right. x1, so this term does not really change. So, for example, ax equal to x when lambda equal to 1. So, you say a power 100 times x is also equal to x. So, this is in the control language could be called as this is like corresponds to the steady state, right, where if I am a steady state I just be there for like forever, right. This corresponds to the eigenvalue of lambda equal to 1. And just say I have a scalar system xk plus 1 is a times xk where a equal to 1, right. This will correspond to something like this, right. I will just be at the initial condition for all times k greater than or equal to 0. The second term is, if you see with time it just gets decaying. You can just visualize this as, let us say I just call this, let me call this x1 and let me call this x2 k plus 1 is some number which is say 1 by 2 xk. As time grows this just decays, right. So, this we should have something like this. So, this is the second term is called usually, or this term is the decaying mode. Right, and at steady state it just converges to values like this. Okay. Now, what happens for some other values, right. So, we just assume things were very nice here, but what if this number a is greater than 1, if x k plus 1 is say 2 times xk, then you kind of grow exponentially. Similarly, if my eigenvalue lambda is minus 1 instead of plus 1, then I have xk plus 1 is say minus of xk, then I will just be switching between plus 1 and minus 1 and there will actually be no steady state that will exist, right, and so on. So, these are essentially, so if I were to look at this in terms of poles of the system, this would be called as a marginally stable system in the discrete sense. So, we may at the moment not really know the definitions or the interpretations of stability, but the way the system behaves at steady state shows that it is a marginally stable system, that I am just at a particular, I just reach a constant non-zero value. What if both the eigenvalues are less than 0, say lambda 1 is 0.5, lambda 2 is 0.8, then at steady state both x1 and x2 will actually go to 0, because everything will have the decimal number raised to a very high power, asymptotically, right. Okay. in literature this is also referred to as the Markov matrix, and what we see is that my values converge to the eigenvector corresponding to the eigenvalue 1, which is possibly the largest eigenvalue. Anything larger than 1, I am looking at an unstable system. So I would not really worry about convergence over there, because it is just an unstable behavior. Okay, so after we are done defining eigenvalues, eigenvectors, and the corresponding eigenspaces, let us see if there is a relation between invariant subspace and also a similarity transformation. Okay, let us start again with f from Rn to Rn. Let it be a transformation with an equivalent matrix representation by A, and let S be F invariant, where S is an m dimensional subspace of Rn. Okay. So, what does this mean? That if I take an element x which belongs to S, this also implies that A times x will also be in S, right, and S is a subspace of Rn. Okay. Now, if S is an n dimensional subspace, it will have n independent, or let V1 till Vm be basis vectors for this subspace, right, and let me denote this Vn cross m matrix in the following way, right. So, I just collect all the basis vectors V1 till Vm and call this matrix as Vn cross m. Okay. Now, any Vi will be an element of S because of its invariance, and each AVI can be written as a linear combination of basis elements of S, right. So, let us see this again, right. So, I am taking one basis vector Vi, A times Vi will always be an element of S, right, because of the invariance property of S, and we know that each element of S can be written as a linear combination of its basis vectors, right. So, AVI, which is an element now of S, can be written as a linear combination of these basis vectors V1 till Vm, okay, and I can just write an equivalent matrix representation of this like this, okay. And I can in general now write for all V, right. So, for this entire thing here, A times V will be equal to V A bar, okay. So, this V, so similarly like here, right. So, I can just generalize this to write it as AV is V, which is an n cross m matrix coming from here, and a matrix A which is an m cross m matrix. So, you can write that down, and it's a pretty obvious relationship to derive. Okay. So, let me now construct a matrix T which comprises, or its first m rows are V1 till Vm, which form a basis for S. Okay. Let me always let me write down some n minus m vectors in such a way that this set of V1 till Vm, and okay, let me call this say U1 till Un minus m, let this be a matrix whose columns are basis for Rn. I can always do this, right. You give me say m or m independent vectors, I can always write the remaining n minus m vectors such that they are linearly independent of each other, okay. And then A times T can be written in this way, A, U and V, where T is actually U, V and U, right, this one, okay. So, A times T is now a matrix which has components AV and AU, okay. So, A times T, now I go back here and exploit this relationship. A times V is V A bar, okay. This can now be written as A times T as T A bar and 0 and T inverse. I just multiply by T and its inverse, and this is obvious to check because T has a representation of V and U, okay. So, I can equivalently write this as this, okay. So, now what I have is A times T is T A bar and 0, T inverse A bar and U, okay. So, now from this I can write T inverse AT So, I just get this on the other side. So, what I am left with here, so this T also goes here. So, I have T inverse A T. So, just concentrate on this term. This is the term of interest. So, I have A bar, I have 0 and certain terms here A 1 2 and A 2 2. This could be whatever. Okay. So, what does it mean that, so this, the invariant subspace of A results in a similarity transformation as we just derived. Okay, what is the importance of this? The importance of this will be seen when we decompose a given system into its controllable and uncontrollable components. So, that and similarly with observable and non-observable components. So, we will remember this and use this as a basis to generate what is called as controllable subspaces. Okay. So, to end this lecture, so what we saw was the concept of invariant subspaces, eigenvalues and eigenvectors. In the next lecture, we will talk about diagonalization, generalized eigenvectors, the Jordan form and the singular value decomposition. These are also would be instrumental in simplifying complex matrix computations. So, that's coming up in the next lecture. Thank you.